Sadly, in these problems, it's not often that we see just a single charge having some effect on a single other charge. They typically come in sets. We have lots of charges, and we could have them arranged different ways, and so we need to know how to handle that in terms of both electric fields and electric forces. Now, electric fields and forces are both vectors. So if we have several electric fields that are overlapping or that are affecting a single point in space, we're just going to use vector addition with those individual values to figure out what the resultant electric field for that location would be. So we'll practice that on this old AP exam question, 1993 one, so even before my time taking the AP exam, so a few years back, but still a good question. So the idea here is that we have this arrangement where we have two charges that are just shown on the axes here so we can tell where they are. And we're asked to find the electric field at the origin for the first charge caused by the first charge and the field caused by the second charge, and then the overall electric field at that location. So, to do that, we have the equation for the electric field of a point charge is equal to 1 over 4 pi epsilon naught times q over r squared. Okay, so let's do charge 1 first. So here our Q value is the negative 16 times 10 to the negative 6th coulombs, or negative 16 microcoulombs is how we normally read that. So E is equal to the 1 over 4 pi epsilon naught. Remember that's one given as one constant in the on the equation sheet. So that's 9.0 times 10 to the 9th newtons. It's 1 over 4 pi epsilon naught. Oh, I was right. Newton meters squared per coulomb squared. There we go. Times our charge is negative. Oh, I misread that. Negative 1.6 times 10 to the negative 6th. That's coulombs. And then divided by our distance here, looks like 4 meters. Yep, 4 meters away. So that gets squared. So 4 meters squared. Okay, and typing this into the calculator now. So 9 times 10 to the 9th times a negative 1.6 times 10 to the negative 6th divided by 4 squared is just 16. And we get a negative 900. And the units there are newtons per coulomb. And remember that the negative 900, the negative part means that this is an attractive force or a field that goes toward that charge. So here, let's do this in another color so we can see it a little better. From this location, we have E1, which is 900 newtons per coulomb toward Q1. Okay, and then we'll go to the second problem. So same equation. So E is going to be equal to 9.0 times 10 to the 9th Newton meters squared per coulomb squared times the charge of the second one here. That's 9.0 times 10 to the negative 6th. That's coulombs. Divided by our distance, which is 3 meters, and that gets squared. Okay, so 9 times 10 to the 9th times 9 times 10 to the negative 6th divided by 9. A lot of 9's in that equation, and we've got just 9,000 newtons per coulomb, and that's a positive 9,000. So that means that's pointing away from Q2. Okay, so E2 is equal to 9,000 newtons per coulomb here. Okay, so we've gotten each of those individually. Next step is to figure out what the overall electric field at that location would be. So you can see we've got these two vectors. We're just going to do vector addition to figure this out. So part 3, switch back to black here. So we've got to the right 900 newtons per coulomb, and then downward we've got 9,000 newtons per coulomb. So our overall force is going to be down like this. Sorry, overall electric field is going to be down like this. I suppose I should have labeled this E1 and E2. And this one is just E. That's how the problem was set. And then some angle theta. So now E squared is going to be equal to the 900 newtons per coulomb squared plus the 9,000 newtons per coulomb squared. So then E is equal to 900 squared plus 9,000 squared, and to the 0.5 power, we get 9,045 newtons per coulomb. Theta is going to be equal to the inverse tangent of 9,000 over 900, or just the inverse tangent of 10, which gives us 84 degrees. So then E is equal to 9,045 newtons per coulomb at 84 degrees. And this doesn't really give us northeast, southwest here, but we'll go ahead and use those conventions. So north would be up, east is to the right, south is down, so this would be south of east. Oops. Okay. The next warning target, 104, just says we need to now be able to take this electric field and figure out what the electric force would be. Well, force is just equal to the electric field times the charge. So this would be equal to 9,045 newtons per coulomb times the charge of, oh gosh, I forgot to show us what the charge was. Okay, so we put some third charge here. There's no force without a charge there. There's just the electric field. So we put some third charge right here at the origin. That's where Q3 is going to be. And we're looking for the electric force now. Okay, so the electric field was equal to 9,045 newtons per coulomb at 84 degrees south of east. Now the electric force is equal to the electric field times the charge. So if we're looking just at magnitudes to begin with, we'll have 9,045 newtons per coulomb times the charge, negative 4 times 10 to the negative 6th coulombs. And we get, let's see, 9,045 times negative 4 times 10 to the negative 6th. And we get negative 0.036 newtons. And the direction here is 84 degrees south of east, but with the negative sign there, instead of 84 degrees south of east like this, it's actually going to be the other direction, so that'll be 84 degrees north of west. So this force, just opposite direction because of the negative sign there. 0.036 newtons at 84 degrees north of west.